I will talk about the maximum tangencies among planar curves. So let's start with some terms and assumptions that we will use. So by a curve, I mean a Jordan arc, so a simple planar curve between two endpoints. And by a closed curve, I mean a Jordan curve. And we will assume that every two curves intersect at finitely many points, so we don't allow such overlaps like here. Can you see my pointer, by the way? Good.
Yes.
So any two points have finitely many common points, and these points can be either crossing points, and if they are not crossing points, then we call them tangencies, tangency points or touching points, like in this example over here. And we say that two curves or two regions are tangent if they have exactly one point in common, and this point is a tangency point. So, for example, these two curves have a tangency point, but also a crossing point, so we don't consider this case to be a tangency. And we will consider several classes of curves. One of them is k-intersecting curves, which are families of curves in which every pair of curves intersect at most k points. If we have k equal 1, then we call one intersecting curves also pseudo-segments. And if we have two intersecting closed curves, we call them pseudo-circles. We will also consider x-monotone curves, which are curves that are intersected by every vertical line at most one. So the one on the right is not an x-monotone curve because it is crossed twice by this vertical line, and the left one is an x-monotone curve. And one last term for now is the tangency graph of a set of curves or regions where the vertices represent the curves and the edges represent the tangent pairs. And we will be interested in the maximum number of tangencies among n curves or regions that satisfy some given property. Now, these problems have been studied before, sometimes explicitly, sometimes implicitly. So, for example, we can consider the tangency graph of interior disjoint disks. This is called the coin graph because you can take coins, place them like on the table, and ask for the maximum number of tangencies between the coins, and you don't allow coins to overlap. And it's easy to see that this graph is planar. You can place a vertex at the center of every coin and connect centers of tangent coins by a straight line segment. So you get a planar graph. And by the circle packing theorem, it also works the other way. If you have a planar graph, then you can realize it as a tangency graph of interior disjoint disk or of coins.
By the way, I
So
like the picture. I mean, did you make it yourself? The coins?
yes, I drew all the pictures by myself, except for one. Maybe I will mention it later.
So you took a photo of some coins on the table or something like that?
So I copy and paste several coins.
Ah, nice, nice.
I'm glad that you appreciate it. Okay, so as a corollary, we get that the maximum number of tangencies in this case is 3n minus 6, because this is the maximum number of edges in a planar graph. Now, this is another picture I made myself. This time we consider points of the same size, for example, penny coins. And again, this problem has been studied, and it was shown that the maximum number of tangencies between n interior disjoint unidisks is this expression here, 3n minus square root of 12n minus 3. And again, you can place a vertex at the center of every penny and connect the centers of touching pennies. And then you get what is known as a matchstick graph. So if these pennies have a radius of a unit radius, and the distance between two neighboring centers would be 2, but you can scale it and get a distance of 1. So this is basically the definition of matchstick graph. It's a planar graph, and the length of every edge is exactly 1. Now, if we drop this condition that the graph is planar, then we get the famous unit distance problem of Erdős, which asks for the maximum number of pairs at unit distance apart among endpoints in the plane. And again, you can so every point can be the center of a unit disk, or more precisely, a disk of radius 1f. And then you can just ask for the maximum number of tangencies among n unit disks, because you can scale it by 2. So this is an equivalent phrasing of the unit disk problem. So this is a far more difficult problem, for which we all know some superlinear lower bound and then an upper bound of n to the 4/3. Tangencies are also related to digons. These are faces of size 2. And in several cases, you can interchange between tangencies and digons. So, for example, going from tangencies to digon is easy. If you have this set of circles and you say inflate every circle a little bit, then you get a digon for every tangency. And sometimes it's also easy to get from digons to tangency points. Like, for example, in this case of curves, you can redraw them such that the digons become tangencies, like in this example. So many times you can interchange the two, and people were interested in counting or bounding the number of digons. So one reason is that if you want to turn a family of 2 intersecting curves into 1 intersecting curve by cutting some of the curves, and you want to use as few cuts as possible, then the lower bound is the number of digons. So people have studied this problem. To be honest, they were more interested in the number of non-overlapping lenses, which are this creature over here, which I will not define, but also in the number of digons. Okay, so going back to the problem, we ask for the maximum number of tangencies among n curves or regions that satisfy a given property. Now, if there is no given property, then we can just have n choose 2 tangent pairs, because all the curves, we can draw them touching at the same point. So let's forbid this. So from now on, let's assume that no 3 curves intersect at a single point. So maybe in this case, you cannot get n choose 2, but you can still get a quadratic number of tangent pairs. For example, if you take n/2 segments, the black ones in this figure, and you can take n/2 convex polygons such that each polygon touches each segment, so the total number of tangencies would be still quadratic, and n²/4. Now, one thing to note about this example is that we have 2 convex families, the segments and the polygons. And the member of one family, the segments, they are pairwise disjoint. and they intersect the polygons, each polygon at most once, actually exactly once. So one can ask, if we force the other family to also satisfy one of these properties, can we get fewer tangencies? And indeed, the answer is yes. So this problem was studied by Pach, Suk, and Tremel, and they show that if you have two families of disjoint convex regions, so if you look at the intersection graphs of the region, it's a bipartite graph, then the number of tendencies is at most 4n minus some constant. And they also have an almost matching lower bound of 3n minus square root of n. You can show the construction. You can see the construction here. So you have like two sets of hexagons. So the red ones are pairwise disjoint and the blue ones are pairwise disjoint. And every red or blue polygon, hexagon touches, so let's say a red hexagon touches exactly 6 blue hexagon, except for the ones on the boundaries. This is where you get the minus square root of n from. So the total number of tendencies is 3n minus square root of n. So there is a small gap between the lower bound and the upper bound, and I was managed to squeeze in this gap and find the exact or almost exact up to some constant bound, which is 3n minus some constant. So improving both the upper bound and the lower bound. And actually the result is a bit more general, because instead of considering bipartite intersection graph, it's enough to consider a K3-free graph. And this actually settles the first non-trivial case in their conjecture that if the intersection graph is KT-free, then the number of tangencies is linear. Again, in this setting of disjoint families of convex regions. So what happens if we don't consider convex regions, or we just consider bipartite intersection graph? So in this case, we still get a sub-quadratic upper bound by an observation of Bendan and Rom, and a recent result of Yancer, Metuko, and Tardosh. Such a family will have at most n to the power of 3f tangencies. And in this case, you cannot opt for a linear number of tangencies, because Kezek and Palvoli show that there are families of anchors with a bipartite intersection graph that admit n to the power of 4 or 3 tangencies. And their construction is based on the point line incidences with this many incidences between points and line. So it's quite easy to somewhat perturb or redraw the lines as curve and replace every point with a curve that touches all the curves that represent the line incident to this point. Now, in this case, they had to work harder because they want the curves that represent the line to be disjoint, but it is possible to do so. And I mean, we will frequently see this lower bound in this talk, and in all cases, it's based on the point line incidences construction. And they conjecture that this bound should be tight. Now, if you add the restriction that the curves are one intersecting, then in a joint work with Kezek and Palvoli, we showed that the number of tangencies drop to linear. But if you allow two intersecting curve, then it's superlinear. So there is a construction with roughly n log n tangencies, and you can also realize it by x-monotone curves. And it also turns out that this bound is tight, because if you know that the curves are x monotones, then even if you allow many intersections between them, still the number of tangencies is at most n log n, again a result of Kazakh and Palvol. Okay, so that was about disjoint families of curves. So now let's move to arbitrary families of curves. So we don't assume that the intersection graph is bipartite anymore. And for k-intersecting curves, we have, again, these are curves such that every two intersect at most k points. And we have this general upper bound, again, by Kazakh and Palvoli, which is n to the power of 2 minus 1 over k plus 3. And as you might expect, the proof is to show by showing that the tangency graph avoids a certain complete bipartite graph, k plus 3, and some constant that depends only on k, and then apply the Kováry-Sós-Turel theorem. And so this is for every k, and if you take k equal 1, you go to the case of a pseudo-segment, then the result gives the bound of n to the power of 7 over 4. And again, in this case, we have a lower bound from the point line incidences of n to the power of 4 over 3. And in a recent work with Kazakh, we improved the upper bound for this case to n to the power of 5 over 3. And to prove this result, we considered sort of a special case of grounded curves, and then we proved some graph theoretic result. So let me describe these two ingredients. So we said that a set of curves is grounded at some other curve. So take a look at this figure here. So the blue ones are grounded at the red one because every blue curve has at least one endpoint on the red one. So these curves are grounded. And for the special case of one set of curves which is grounded at one curve, and another set of curves which is grounded at another curve, such that all the curves together form a family of pseudo-segments, then we have an upper bound on the number of tangents paired from different sets, which is the size, total size of the sets to the power of 3 over 2. So this is one ingredient of the proof. And usually when you see this bound 3 over 2, then you show that some graph or tangency graph in this case is a k2 something 3, but not in this case. Here we had to use a different result about intersection reverse sequences, and this will be this is actually the reason we needed the other result, the graph theoretical result. So let me describe this result here, and to describe it I need the following definition. So we have a non-negative and non-decreasing function f, and we have a bipartite graph G, and we look at two vertices u and v, and we look at their neighborhoods. Now, if it's true that for every subset of their neighborhoods, the number of edges in the graph which is induced by these subsets is at most f of the total size of the subset, then we say that these two vertices have f sparse sub-neighborhood. So this is the term. And the theorem says it's we call it an Erdős-Simonovitch type theorem for reason that I will soon explain. And the theorem says that if you have a bipartite graph, and every pair of adjacent edges have f sparse sub-neighborhoods, where f of x is order of x to the power of 2 minus alpha for some alpha. So basically it says that you have this local sparsity property. Then you can get a global sparsity property, which means that the number of edges in the graph is at most the number of vertices to the power of 2 minus alpha over alpha plus 1. So for example, if f of x is x to the power of 3 over 2, so alpha is equal to 1f, which is actually the value that we need, then the total number of edges would be the number of vertices to the power of 5 over 3. And the way we use these two results, then it's to get this n to the power of 5 over 3 bound on the number of tangencies among n pseudo-segments.
By the way, the previous theorem is tight, the bound in the previous slide.
So the question is whether this bound is tight.
Yeah.
What was the question?
Yes.
Yeah, so I will get to it later.
Okay.
But the answer is yes. Okay, so we just need to show that the tangency graph has this f-sparseness sub-neighborhood property with alpha equal 1/2. So given two curves, we want to show that the number of tangencies between their neighbors is that much, the total number of neighbors to the power 3 over 2. And this is so we can cut every neighbor of u and v. So for example, I can cut this red curve into two curves. So both of them are grounded at v. So we do it for every neighbor of u and v, and then we get the setting of grounded curves, and we can apply the theorem about grounded curves, and then apply the Erdős-Simonovitz type theorem. And this completes the proof. So why is it called the Erdős-Simonovitz type theorem? So I should say what is the Erdős-Simonovitz theorem. So first, I need to define two terms. One is the extremal function of n and some graph H, which is the maximum size of an H-free n-vertex graph. And in the other one, so suppose you have a bipartite graph H. So by H plus, I denote the following graph. We add to H two vertices, one to each side of H, and connect them to all the vertices on the other side. So H plus is also bipartite. And the theorem of Erdős and Simonovitz from the 70s says that if H is a bipartite graph with at least one edge, and the extremal function of n and H is n to the power of 2 minus alpha for some alpha between 0 and 1, then the extremal function of n and H plus is n to the power of 2 minus alpha over alpha plus 1. Okay, so note that if your graph is H plus free, then it means that adjacent vertices have H-free sub-neighborhoods. Because otherwise you get H plus as a subgraph. So basically it says that if the sub-neighborhoods are sparse because they are H-free, then you get the global sparseness of the entire graph because of H plus freeness. So in our case, the sparseness of the sub-neighborhoods can be for any reason. And remember that we couldn't prove that the tangency graph avoids K2 something. So this is the reason we needed this result. So if the neighborhoods are, or the sub-neighborhoods are sparse for any reason, then we get the global sparseness result. So our result actually implies the result of Erdős and Simonovitz, and their result in turn implies the Kováry-Schuss-Turen theorem, at least the symmetric case, just by using induction and noting that if you take a KTT and apply this plus operation, you add two adjacent vertices and connect them to all the vertices on the other side, then you get KT plus 1, T plus 1. So So it is known that the Kovács-Sós theorem is tight for t equals 2 and 3, but it is a major open problem whether it is tight for every t. And this implies that our theorem, our Ehlers-Shimonovich type theorem, is tight for alpha 1 and alpha 1f. And assuming that the bound in the Kovács-Sós theorem is indeed tight, then for every alpha of the form 1 over t. But somewhat surprisingly, we managed to prove a tightness for every alpha. And the proof is not very difficult. You take a random bipartite graph and you show that with high probability you have this F sparseness property. And actually, I used AI for the analysis of this random graph, showing that it has this F sparseness property. So, I mean, it took several tries and errors with Gemini, but finally he managed to do it and saved me some more. So one final remark about this theorem. So we needed to assume that the sparseness holds for every sub-neighborhood. But we believe that it's not really needed for every sub-neighborhood. You can assume it just for the entire neighborhood. So if I go back to this definition, so it's enough to consider the neighbors of V and the neighbors of U, not every subset of their neighbors. So if you have this property for the neighbors of U and the neighbors of V, it doesn't imply that it holds for every subset, but we believe that this is enough to have the same result. So yeah, I write it here as a conjecture. So it's enough to consider the sparseness between the neighborhoods and not consider every sub-neighborhood. Okay, going back to tangencies between curves, again, considering pseudo-segments. So remember that we have an upper bound of n to the power of 5 over 3 and lower bound of n to the power of 4 over 3. But Pach conjecture that in the case that the pseudo-segments are pairwise intersecting, so every two either cross or are tangent, then the number of tangencies should be linear. So this conjecture is still open. It was proved for two special cases. One of them is when the endpoints of the curves, they all lie in a fixed and bounded number of cells of the arrangement of the curve. So it's a very special case. And together again with Kezek, we proved that this conjecture holds for x-monotone curves. So this is yeah, so that's also for x-monotone curves, but in the general setting, when the curves are not necessarily x-monotone, so far the best upper bound was just the general bound for k intersecting curves that gives the n to the power of 7 over 4. And it follows from our result that you can improve it to n to the power of 3 over 2 because you can just apply the result for grounded curves. So we don't really use this strong property that every pair of curves intersect, just that they are grounded. I mean, you can just pick one of the curves and everyone is grounded on this curve. So there is much room for improvement in this case. So still staying with a pseudo-segment, this time x-monotone pseudo-segment. So they are no longer have to be pairwise intersecting because this case is solved, or at least asymptotically solved. There is a result, or actually it follows from a result of Pach and Sharir from the 90s. They considered a different problem, but the reductions between these two problems are quite easy. And it follows from the result that the maximum number of tangencies among n x-monotone pseudo-segment is at least n to the power of 4 over 3. Again, this point line incidence construction. And the upper bound is not that far. It's n to the power of 4 over 3 times. So there is a factor of log n to the power of 2 over 3. And we managed to shave a log n to the power of 1/3 from the upper bound. So it joint work with Kezek and Pinchasi, but Pinchasi chose to, didn't want to be associated with us. So yeah, we had to cross his name. And for the special case where the curves are grounded, then we have an asymptotically tied bound of n to the power 4/3. So by grounded, I mean for x-monotone curves, I mean that they all have their left endpoints on a common vertical line. So again, the lower bound comes from the point line incidences, and for the upper bound, let me give you some detail about the upper bound. So it is enough to consider the special case where you have red and blue curves, x-monotone, grounded x-monotone curves. Pseudo-segments, and all the red ones start above the blue ones. So their left endpoints are above the left endpoints of the blue ones. So it's enough to prove the bound for this case, and then we just use divide and conquer and induction and conclude also the general case. So to prove this case, we consider pseudo lines and also use the cutting lemma for the case of x-monotone pseudo segments. Okay, so the first lemma, so now we consider pseudo lines. So the pseudo segments are B infinite. They are infinite in both directions. And for this case, it's easy to show that the maximum number of red-blue tangencies is n minus 1. Let me show you the proof because it's very easy. So we mark the leftmost red-blue tangency point on every curve, and we claim that every tangency point is marked, because otherwise, if there is a tangency point which is not marked, so it's not the leftmost on neither of them, so there has to be a tangency point here of the blue curves with another red curve, and there has to be maybe here or here a tangency point of another blue curve with our red curve, but this cannot happen because this blue curve has to start above all the red curves, and on the other end, it is by infinite, so it should escape somewhere here. So there should be two intersections. So this is the first lemma. Another lemma is about pseudo lines, and so we have red pseudo lines and blue pseudo segments, and their tangency graph can be shown to be K3, 2, 3. So there are no three red pseudo lines that are all tangent to the same two blue pseudo segments. It's not hard to show. And the last ingredient is the cutting lemma. So you probably know it for lines, but it also works for x-monotone pseudo segments. So we can choose a subset of the segments such that they define a partition of the plane into trapezoid. So we shoot rays upwards and downwards from every endpoint and every crossing point, and we get partition into trapezoids. And the number of trapezoid is order of r squared, and we have the property that every trapezoid is cut or intersected by at most n over r pseudo segments, and we can choose r to be any number. So we use this cutting lemma with r equal to n to the power of 1/3, and then we consider the number of tangencies within every trapezoid, and we consider the curves that cut the trapezoid as long curves which cut through the trapezoid, and short curves which have one of their endpoints inside the trapezoid. And for the number of long tangencies, we use lemma 1, which talked about pseudo lines, so we can extend them to pseudo lines and use lemma 1. And for the number of long short tangencies, we can use lemma 2 that says that their tangency graph is K2 something, K2 3 3, and then use a Kovari-Shoshtouran. And for the number of short tangencies, we just use induction and then sum everything up, and we get this bound. So this is about grounded x-monotone pseudo-segments, and the final result that I want to mention is about pairwise intersecting pseudo-circles. So pseudo-circles, again, are two intersecting closed curves. And according to conjecture by Greenbaum from the 70s, the maximum number of tangencies among n pairwise intersecting pseudo-circles is 2n minus 2. And these examples show that this bound, if it's true, it's tight, because you can always add another. So every new pseudo-circle that you add intersects everyone and add two tangency points. So actually this conjecture was phrased for digons, but in this case, digons and tangencies are, you can interchange them. And in a work with Damashti, Kezek, Pinchasi, and Rafai, we proved that Greenbaum's conjecture holds. So let me tell you some details about this proof, just a general idea. So the idea is to draw a double tangency graph. So we have two vertices for every pseudo-circle. So for every pseudo-circle, let's call it A, we have two vertices, A in and A out. We chose those names for a reason that will soon be clear. And we have two edges, A out B in and B out A in for every tangent pair A and B. So two vertices and two edges for every edge. And by definition, this graph is bipartite because an edge is always between an out vertex and an in vertex. And if we can show that this graph is planar, then it means that the number of edges is at most twice the number of vertices minus 4, but the number of vertices is 2n because we doubled every vertex. So it is at most 4n minus 4. And since we have two edges for every tangency, it follows that the number of tangencies is 2n minus 2. So Adam, how am I doing in terms of time?
You're completely fine. Do you know how long do you want to keep going?
I guess 5 to 10 minutes.
Yeah, absolutely.
If I go into details a bit more here. Okay, so
whatever you want.
If no one objects, then I will tell you a little bit more details, not much. Okay, so how do we draw this tangency graph? So as I said, we have two vertices for every pseudo-circle, and we do it by adding a new pseudo-circle that intersects every original pseudo-circle that's C in this drawing. And we also orient C clockwise or counterclockwise arbitrarily, doesn't matter. So if you consider a pseudo-circle A, then there is the pseudo-disk which is bounded by A. So at some point C goes inside this pseudo-disk, and this would be A in, and at some point it goes out, and this would be A out. And we do the same for every pseudo-circle. So these are the vertices. And for the edges, there should be an edge. If A and B are tangents, there should be an edge between A out and B in, and also between B out and A in. And we draw them following more or less this new pseudo-circle C. But we need to make a decision at every vertex if we bypass it from the right, like here, or to the left. And so we have a rule for that. So let's say that now I'm at D in. So I look at the pseudo-disk which is bounded by C. And I follow into this pseudo-disk. And then because every pair of pseudo-circle intersect, at some point I should meet B, at some point I should meet A. So in this case, first I meet B, and then the rule that I go from the right, and if I first meet A, then I go from the left. So this is the rule. I'm bluffing a little bit wrong, so don't correct me. And then it can be shown that in this drawing, independent edges cross evenly, an even number of times, and then you can use the strong Hanani-Tat theorem, which says that a graph is planar if and only if it can be drawn such that independent edges cross an even number of times. And then this completes the proof. Okay, so so this table summarizes most of the results that I've mentioned. There are some that I didn't mention. So for example, for pseudo lines, it can be shown. So we know the asymptotic tight bond, number of tangencies between them. Also for pairwise intersecting pseudo lines. And of course, the open problem is to close the gap between the upper and the lower bound. So for example, it would be nice to get rid of this log n to the power of 1/3 for x-monotone pseudo-segment. And I think the most interesting case is the one that I already mentioned. So pairwise intersecting pseudo-segments. We have this conjecture by Pach that the bound should be linear, but we only have an upper bound of n to the power of 3f's. And I also want to mention this conjecture. So suppose that you have n pairwise intersecting x-monotone k-intersecting b-infinite curves. Then we conjecture that the number of tangencies should be linear in this case. And if this is true, then it's also true if they are not bi-infinite. Because you can get from non-bi-infinite to bi-infinite just by adding at most 2 crossings per pair of curves. Okay, and a few other 2 other results and open problems. So you can consider tangencies among plane algebraic curves. Yes, this was done by Ellenberg, Shoimoshi, and Zal. And their notion of tangency is a bit different than what I described. So for example, they allow tangent curve to also cross at other points. So in this sense, it's more general. And then they show that in this case, they can upper bound the number of tangencies by n to the power of 3/2. But again, there's a gap from the lower bound of n to the power of 4/3. And there is also a result by Pachum and Tardosh. They basically settled a long-standing conjecture by Richter and Thomassen. So suppose that you have n pairwise intersecting closed curves, but they can intersect many times between them. And again, you allow them to be tangent and also cross. And you count the number of crossings and the number of tangency points. So the conjecture was that there are many more crossings than tangencies. And indeed, they proved that the number of crossing is at least t, the number of tangencies, times log n to the power of 1/8. And the conjecture that it is at least t times log n. Okay, I think that's it. Thank you for your attention.